All right, so the median, the mean was a 47. Let's see. I'm going to avoid telling you what your grade is as a function of your score, because a lot of times the how you do on the midterm does not reflect the final grade, and people come back and say, I thought I was in this ballpark or that ballpark. So I'm going to refrain from saying too much about that. Although I'll say this, the median is about a B. Okay, so I like to give half the class B or better. That's for undergrad. Okay, for grad, I mean, an undergrad is going to think this kind of sucks, but it's about B plus, A minus. The reason being that grad students have to get a B. B is equivalent to pass. So in some sense, you're not really in competition with one another. The graded on a separate scale. Sorry, B plus. Okay, and let me make some other comments. You know, when you give a midterm, you always sort of suspect how people are going to do, and then you're always surprised at what they get and what they don't get. So people did very well on the third problem in general, especially 3C. I think people took a shortcut, which I don't think will work all the time. But if you use that shortcut and you got the answer right, I didn't penalize you for it. On the other hand, so question 3 was the 3 wireless devices using CDMA codes. And 3 people did well in general on all parts. Question 2, most people got the right idea. And the one that people are going to be very unhappy about how I graded is going to be B, where I asked for the Hamming distance. The correct answer was 4, but I didn't care all that if you got the correct answer. I cared how you got the answer. And if you applied a method that didn't work, you didn't get credit. Okay? So a lot of people took the rows of the check matrix and showed that the Hamming distance between rows of the check matrix is at least 4. That's not sufficient. Happened to be true in this case. I can easily come up with a code with a Hamming distance of 3, where you take the Hamming distance of the words in the check matrix, you get 4. Other people listed all the words in the code, all 16, and said, by comparing all these, I can see the Hamming distance is 4. I mean, come on, you compared 16 choose 2 combinations? I don't believe it. Without showing any scratch work? I didn't buy that either. So the way to do it was to look at the columns of the check matrix. You need at least 4 columns that XOR together. You can't XOR a bunch of, you want to XOR a group of columns together such that the columns XOR to 0. You needed at least 4 columns to do that. That was the right way to do the problem, so that was sort of an all or nothing. I guess sometimes if people, sometimes I gave out partial credit. But that's really what I was looking for. That's really the only feasible way I could be doing this in the time allowed. Otherwise, I thought I didn't buy your answer. So I unilaterally didn't buy the answer, unless it was done that way. And very few people did it right. Also, 1D. Very few people got that right. I think maybe 2 people got it right. It was the conditional probability. I mean, it's funny. Again, at the beginning, first day of class, I said, remember, it's defined this way. Use the definition. And people right away just sort of ignored the definition and started doing, probability of A conditioned on B plus probability B conditioned on C, C conditioned on D. Where they had different conditions, and that wasn't the way to do it. I mean, if you just went by the strict definition, it was some simple permutations you could have done. Some people also weren't careful. I mean, maybe for people in CVN, I can be a little more tolerant of this, but in class, when you're taking the exam, I pointed out, It's the check that can flip. The check bit can flip. At most, one check bit can flip. So any number of data bits can flip. And a bunch of people still didn't seem to understand that. So you could have had one check bit and 3 data bits flip, one check bit and 2 data bits flip, one check bit and no data bits flip, no check bits and 4 data bits flip, no check bits 3, et cetera, et cetera. So, all right, let me hand these back. And office hours today, I have to postpone because I have a visitor at 11. So if you have questions on the exam, send me email. And we can meet later in the day, tomorrow, etc. Or 11:30, I should be available as well. If you want to come by my office at 11:30, that's fine too. Actually, 11:40 because I got to walk the visitor to another office. So let me say 11:40. And if I'm a little late, don't worry. Yeah. 78 to 16. Okay. The grades were somewhat clustered though. So, and in case people are wondering, the high grade I think was 75. Okay. So let me start handing these back. And forgive me in advance for mispronouncing names. And these are being returned in no order whatsoever. So not in sorted order, by score, not by alphabetical order. As a Rubenstein, I never liked it when they did things in alphabetical order. So my cousin liked it even less. His name was Zagelbaum. So okay. Aluwarotimi? Venkata Sastry? Patrick Rausch? Faisal? Chenan? Ben Lee? Ron? Shu Cheng? George? Emil? Amy Fernandez? Jason Cardijo? Pacerini? Gary Lowe? Ari? Yusung? Yusung Lee? Iwei? Akshay? Ben? Sivaram? Pamela? Binjang? Sapna? Chi Tai Chow? Akira? Yushan? Ezra? Shang? Yang Duan? David? Hover? Nancy? Alexander Kuo? Jun Hao? Chi Kang? Philip Lee? Shu Ching? Gary Lowe? Ari Klein? Ben Dwight? Okay. And Aluwarotimi. Okay. So tell those people I have their midterm, and if they want it, they can come to my office and get it. Anybody have any questions about the midterm? If you have questions about the grading, if you feel I graded you unfairly on something, come and see me. But again, I really tried to enforce the same policy throughout. So, you know, again, I imagine most people will be unhappy with the grading of this question, but we'll see. Okay. Any other questions before we move on? Okay, the midterm really came at a nice point because we're not exactly moving up to the network layer now, but we're transitioning in the kinds of problems we're going to study. So we're going to leave probability behind for a while, and we're going to move into simple graph theory, and of course, how it applies to networks. So we're going to be very interested in things like shortest path tree, minimum spanning tree, because those are used to route through networks a lot of the time. Or if you're going to try and learn how to route through networks, it's the simplest place to start. So who's familiar with these ideas? Shortest path tree, minimum spanning tree. Who's seen this sort of stuff before? I mean, it's pretty common in computer science. Okay, a very small set of people. So probably for you folks, what you're going to see is a lot of review. For everybody else, it'll be somewhat new, apparently. Yeah, Ron. No. But I don't. Well, obviously. So yeah. I'll be handing out a homework on Monday. So homework will be handed out Monday, and it's not due Wednesday. So I have to update the website. I have to rearrange the date. So probably what's going to happen is I was planning to give out 4 more homeworks, or 5 more homeworks. We've only had 3 homeworks, right? So I'll probably there was usually the 4th homework is a very short homework, and this time around we combine the 4th and 5th. So there'll probably be 7 homeworks in total for the class, and the next one will be a big one. Okay, covering a lot of this tree stuff. Okay, so we're going to be looking at a lot of graphs. So if you draw a network, okay, a lot of the time when we talk about routing, we're going to have 2 points. We want to route one point to another point, and there'll be some intermediate routers. Okay, maybe lots of different paths between these two network endpoints. And you want to choose the best route. And if you have a global view, you can sort of see maybe it's something like this. Okay, but without that global view, it becomes a hard problem. So we're going to sort of theorize what a network looks like, looking at it as a graph, and then we're going to study algorithms on those graphs. Okay, so we're going to look at a graph. A graph is, we'll write a graph as G, and it's going to be VE, or V, oops, is a set of nodes or vertices, and that's why V is commonly used. Nodes and vertices are the same thing. They'll be drawn as little circles. And E is a set of edges. Okay, so for instance, here's a simple graph. Okay, so the circles are nodes, and the lines are edges. Okay, this graph happens to not be connected, meaning that there is no path you can take, no series of edges you can follow to get to this node. This node is disconnected from the rest of the graph. Okay, a directed graph is a graph where edges have a direction. So we'll represent it as put a little arrow on the end to indicate the direction of the edge on the graph. So you can always have an undirected graph, and you can put directions on the edges. And in a directed graph, you can label separately. There can be two edges between a pair of nodes, one going in one direction, one going in the other direction. Or you may have just one edge going in one direction. Okay, these are my pathetic attempts to draw arrows. Okay? We're not going to deal so much with direct graphs. But what we are going to deal with is weighted graphs. We're going to deal with a type of weighted graph. Let's call it W. Here are the vertices. Here are the edges. And W is a function that assigns a weight to an edge. A weight. Okay, which is a real value number. To an edge. Okay, so WE is in the reals. Okay, and we can draw that if I draw a weighted graph. So they can be directed or undirected. So let me draw a directed weighted graph. So here are the edge weights. Here are the edges. And then I can assign weights to the edges. 3, 2, pi, square root of 91, 6.7, minus 15, 0. Okay? But we will usually deal with W mapping to positive values. Right? Graphs where the edge weights are non-negative or in fact positive. We usually won't have zero edges. Any questions? Okay, a path. Let's just use a letter. It's a piece of it. Is a sequence. Sequence as opposed to set, because the order is important. Of nodes. Okay, so that means that each pi is in V. Where there is an edge pi minus 1 pi for all 1 less than I less than or equal to m. Okay, so and let me, one thing I forgot to mention. Just some notation. The edge going from node x to y is written x comma y. Okay, so in an undirected graph, right, where you have no arrows on the edges, x, y will be the same as yx. Right, the edges are the same. And we can write w of xy for the weight of edge. xy in a weighted graph. Where x and y are both nodes in the graph. Okay? Okay, so let's see. Okay, so here's an undirected graph. I've labeled the nodes A through G, and let's see, A, B, F, G, A, B, C, D, F, E is a path. In the graph. Okay? I'm taking a path going through this graph. A to B to F to G to A to B to C to D, F to E. Okay? It's definitely the shortest path from A to E because I go through a bunch of cycles, but it's a path. Right? A path P has weight W of P, where let's say P is P1, P2, P sub m. Okay, so when I write this P1, P2, some of these P's can be the same nodes. The same node can appear multiple times in a path. Okay, has weight P, where this is the path, and then WP is going to equal the sum from I equals let's start at P0. P0, P1, dot. So I goes from 1 to m of the weight of the edge P sub I minus 1 P sub I. Right. So the weight of a path is the sum of the weights of the edges that you take along that path. Okay? The path contains a cycle. If Pi equals Pj, for some I not equal to j. Okay. Let's say from I less than j. And the cycle is pi plus 1 dot 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 pj. So basically, in your path, at some point you get to a node, and then you keep going, and then at some point you go back to that node again. Right? That's a cycle. So in this picture we drew up here, we have a couple of cycles. So ABFGA is a cycle, right? Because you started at A and you ended up at A again. BFGAB is a cycle. FGABCDF is a cycle. Okay, can people see that? Okay. The degree, I'm just throwing out terminology here, one after the other. The degree of a node is the number of edges that are attached to that node. Okay, so degree of A, the example above is 2, degree of F is 4, etc. Okay, and in a directed graph, the in degree is the number of edges of a node. The number of edges pointing toward that node right, and the out degree is the number of edges pointing away. Who wants me to draw a picture? I think it's pretty self-explanatory, right? I mean, you can imagine if you have edges on the directions on those nodes, then the ones that point out, that's the out degree. The one pointing toward or in, that's the in degree. Okay, so the in degree of a node plus out degree equals the degree. Let me not say that, because again, if I have a node with one edge going in and one edge going out, in an undirected graph, we would represent that by one edge. So everyone gets degree, in degree, out degree? Who doesn't get it? All right, good. Yeah?
For an undirected graph, there's always a cycle, because we can just go back.
No, and we're gonna get to that next. There isn't always a cycle. So.
Because if it's undirected, you can always go back.
Well, it depends how you draw the graph. You can draw any graph. I mean, if I'm free to draw the graph how I want, I can draw no edges. There's no cycle, or I can draw every node with one edge or two edges, and there's ways to do that without it having a cycle. So I mean, that's actually what we're going to get into now. Okay, well, the graph is connected if there exists a path from every node I to every other node J. Okay, so you remember So for instance, in the directed sense, this graph is not connected because there's no path from this node to any other node. Not allowed to go against the direction of the arrow. Okay? And an undirected graph, if the graph is undirected, you can basically see a partition. You know, there won't be edges connecting. So somewhere there'll be two nodes that aren't connected by an edge. So, well, that's not sufficient to make it undirected. So here's a graph that's connected. Right, this is connected. This is unconnected. Right? There's no way to get from this node to this node, for instance. Or not fully connected, I guess is a better way to put it. Okay, and in the undirected setting, a graph that is connected and has no cycles is called a tree. Okay, a very, very important term for us. Okay, so Emil, here's your example of a graph that has no cycles. No cycles. It's a tree. Okay? The question, Faisal? Okay. Okay, other properties of trees. Can you get why it's called a tree? I mean, it kind of looks like a tree. Because it has, you can imagine there's some node that's the center, or the root, and then it just branches out. Right? Like trees branch out, and you know, if you sort of walk, if you could walk up a tree, if you were a squirrel, okay, and you walked along a tree and started walking along branches, you'd never get back to where you started. At some point you'd reach the end, and you don't loop around. Unless you jump from one branch to the other. Okay, so if you're a squirrel who's very good at climbing branches but is incapable of jumping, and that's the case. Okay, so does anybody see some other properties of trees? So I'll give you a hint. Consider a tree with n nodes. What can we say about that tree? So the n nodes is important. Patrick. The degree of the nodes will be n minus 1. Well, I mean, there I've got on the order of 15 nodes. Okay, the degree of a node will be less than. That's always true. Even if it's not a tree, right? I mean, there's only n minus 1 other nodes to connect to. But you're on the right track. There is something. Some property I'm looking for. Yeah, Sastri. Yeah. There are exactly n minus 1 edges. Okay, that's you can sort of see it by example. It's not so obvious, so we're going to prove that. So we're going in this part of the course we're going to start dealing in proofs. A lot of proof by induction, a lot of proof by contradiction. So, okay, any other properties? So I want something having to do with consider node consider two nodes, I and J, and the paths that connect I and J. What can I say about those paths? There's only one, yes, it's unique. There's only one path. There's only one path from I to J. Okay? How would you prove that? Okay. Yeah, right. So if you have two, right, exactly. If you have two paths between pairs of nodes, you're gonna have a cycle. So the easiest way to prove that, I mean, what you basically said is that's a proof by contradiction, right? It's a so we're going to prove by contradiction. Assume tree T has two paths between nodes I and J. Okay, so let I and let's not use that. I P1, P2, PK, J is the first path, and let's have the second path be I. Let's call it B1, B2, B sub L J, and okay. So one thing is that P1 does not equal B1, and PK does not equal BL. Okay. Otherwise, let I be the P1 and J be let I be P1 instead, right? So instead of starting as node I, we just start here, and I could do the same claim there. I'm starting from the same place, okay? And same thing with PK not equal to BL. Else let J equal PK. So the first steps are different. Okay, so I have a picture like this. I, P1, B1, J, PK, and BL. Okay, and so you can sort of see that what's going to happen is I'm going to go this way, and then I'm going to come back this way and produce a cycle. One subtle point is that all I'm trying to avoid is that you just want to avoid the case where you sort of walk down a path and then walk right back. That's not a cycle. I mean, you're taking the same path that you took before, and that's not considered a cycle. Well, I guess I should say there's only one path from I to J. Yeah, fine. I'll leave it at that. Okay? People follow? Okay, how about proving that a tree has exactly n minus 1 nodes? Sorry, a tree with n nodes has exactly n minus 1 edges. trying to think of the easiest way to prove this. Okay, I know how to prove it. Anybody else have any thoughts? Anyone here not familiar with proof by induction? Who has not heard of proof by induction, or wouldn't know if I said you prove it by induction, what I mean by that? You don't know. Okay. Proof by induction means logicians claim this isn't actually a valid form of proof, but it's sort of a weaker form of proof from a standpoint of logic, but for our purposes and for most mathematically oriented purposes, it's sufficient. So here's the idea: you have a problem with a property or a domain with a structure whose property can be described or uses an integer to describe it, whose property uses an integer to describe it. Look, let me change that again. Proof by induction, you start with a claim that holds for all integers. Okay, so for instance, here our claim is a graph with n nodes. A tree with n nodes has n minus 1 edges. Okay, so the proof by induction is first show holds true for the base case. So for instance, when n equals 1. Then show that given it holds true, for the case where n equals I minus 1, it also holds true for case where n equals I. Okay? So for our problem, so to show a tree with n nodes has n minus 1 edges. Okay? First we'll do the base case, where n equals 1. I've got one node. Obviously, I have no edges. Right? It's obviously true. Now I'm going to assume it holds true for all trees with I equals n minus 1 nodes. Okay, and I've got to show if I have that assumption, I've got to now show that it holds true for all trees with n nodes. Okay? So, to prove this, we're going to need something that we're going to call a leaf node. A leaf node in a tree is a node with degree 1. Okay, very intuitive idea. Here's my tree, leaf node. This is a leaf node. This is a leaf node. This is a leaf node. This is not a leaf node. Okay, this is a leaf node, not a leaf node, not a leaf node. This is a leaf node. So leaf nodes are, again, you think about it as a real tree. If you walk all the way up the branches, the leaf nodes are the ones at the ends. When you walk on this tree and you get to somewhere you can't walk any further without going back, i.e. there's just one edge, you're at a leaf node. Okay? So that's a leaf node. Okay, so I'm gonna prove a bunch of claims. Claim 1. Every tree has at least one leaf node. Okay, we'll prove this later. Okay? Okay, yeah. Claim 2. If a leaf node is removed from a tree and its connecting edges, from a tree T to produce graph T prime, that's a comma, then T prime is connected. Okay, we'll also prove this later. Okay, but it should be intuitive. If I remove a leaf node, the graph is still connected. And basically the proof is I remove this node. There's only one edge connecting it. It's always at the the edge of the branch. It's like if you break a leaf off of a branch off of a tree, right? You're going to disconnect. If you break the very end of the branch off, that's not the way to put it. If I break the end of a branch off and replant it, no, okay, not bad example. Let's just say if I take away a node that's a leaf, okay, you can see I'm not partitioning the tree. It's to do with the fact that there's only one edge there. That edge is used to get from that node to the rest of the tree, and if I remove it, meaning I get rid of it, not I just get rid of the edge, but I get rid of the node itself, this remaining graph is still connected. Right? Okay. So now we're ready to do the inductive step. So start with a tree T with n nodes. Remove a leaf. And an edge, and its attached edge. Which produces graph T prime with n minus 1 nodes, and let's just say E edges. Right? By claim 1, I can do this. I mean, remove a leaf node. Right? By claim 1, there exists a leaf node, so I can remove it. Okay? And by claim 2, T prime is connected. Right? I can still get from any node in T prime to any other node in T prime. Right? And now my claim 3 is that T prime is a tree with n minus 1 nodes. Right, and the proof is T prime is a subgraph, okay, of T. I guess I never defined subgraph, but I should. So we'll do that soon. Subgraph means you have an original graph and you remove nodes and edges, and it's what you're left with. That's a subgraph. T prime is a subgraph of T. Okay, so if T had no cycles, T was a tree, implies that T has no cycles, then T prime can't have cycles. Right? If in the original graph I don't have any cycles, I have no paths that contain loops. If I remove a node, I don't suddenly get paths that have loops, that have cycles. Right? Okay, so T prime has no cycles, is connected, has n minus 1 nodes. Right, that's where we're at. Good question? Question? No? Okay? I must have erased it, but the definition of a tree is a graph that's connected that contains no cycles. Right? So T prime is a tree. With n minus 1 nodes. And now we use our inductive assumption. Which was that a graph with n minus 1 a tree with n minus 1 nodes has n minus 2 edges. Right? T prime has one fewer node and one fewer edge than T. So this is so T prime has n minus 1 nodes, n minus 2 edges. So T, which has one node, and one more edge, then T prime has n nodes and minus 1 edges. So we're done. We proved the inductive step, right? We showed that there was any graph that had one node has 0 edges. And the inductive step says that if you have a graph with n nodes and and we don't know how many edges, but if it turns out to be the case that all trees with n minus 1 nodes, sorry, a tree with n nodes, and we don't know how many edges, but if it turns out that all trees with n minus 1 nodes have n minus 2 edges, then we're able to show that a tree with n nodes must have n minus 1 edges. So it was true for a graph with one node Hence, we can do it for graphs with 2 nodes. All graphs with 2 nodes, you can apply this inductive step, bring it to a graph 1 node. That graph must have 0 edges. Hence, the graph with 2 nodes must have had 1 edge. Then you do the inductive step again. All graphs with 3 nodes, all trees with 3 nodes, you can remove a leaf. Now you're left with a graph with 2 nodes. You can show it's a tree. Therefore, it must have 1 edge. Therefore, the original tree must have had 2 edges, and etc. So you keep applying the inductive step, and so it holds for all trees. People follow the argument? That's induction, proof by induction. Who gets it? Just out of curiosity, who really feels like they get induction, proof by induction? Okay, well, I'll give you two cute puzzles, and you got to figure out one is why the guy could do this, because he's smart and he could do proof by induction, guy or girl, and the other one is sort of a clever example where you got to figure out what's wrong with using proof by induction here. Okay, let's do the second one first because it's easier. So my claim is that all cows are brown. All cows are the same color. Okay? And here's how I do it. The base case. One cow. It's obviously all the same color. Right? And now my inductive step. Suppose I have n cows. And suppose holds true for n minus 1. Okay, so I'm assuming that whenever I have n minus 1 cows, they're all the same color. So now I've got n cows. So I remove 1 cow. I've got n minus 1 cows. By my assumption, they're all the same color. Now I put back that cow and I remove a different cow. Again, by the inductive assumption, they're all the same color. Right? So I had this group of cows. I pulled one out. All these had to be the same color. I pulled one of these out. That's the same color of all the rest. I put this back. They've all got to be the same color. Hence, by induction, all cows are the same color. Okay, so what's wrong with that argument? Huh?
Put the original, the n cow back.
Sure it is. By the inductive assumption. I have n cows. I take one out. Whenever I have a group of n minus 1 cows, by my assumption, they have to be the same color. So they're all the same color. So I take that cow, and now it might be a different color, but all the ones that were left there are the same color. Now I put it back, and I take another cow out. Well, again, I've got n minus 1 cows. They got to be the same color. It is no. I mean, there's something wrong with the proof by induction here. So, what's wrong?
Assumption.
Huh?
The assumption is an assumption that take that one away, the other one below it.
So what's the flaw in that? I mean, holds for n equals 1. What's the flaw? Not bad.
You're assuming that the original group of n cows is all the same color?
Huh?
You're assuming that the original group of n cows is all the same color?
No, I'm assuming that anytime I have a group of n minus 1 cows, they're all the same color. It's true for 1, hence, you know, I apply this argument. I have n cows. I take one out, I have minus 1 cows. If I make the assumption, then it holds for that group of n minus 1. They're all the same color. I put it back. I take out another one. It holds again. It worked the base case.
If you have 2 cows, you remove one, you put the other, you take out 32.
So if I have 2 cows, it still works. If I remove 1 cow, all of them are in the same color. I put it back. I take out another one. They're all the same color. You're on the right track. Okay, so maybe this is the right way to say that the inductive argument does not hold for the case where n equals 2. I mean, think about applying this argument for the case where n equals 2. The assumption was that there was always some cow in the middle that you didn't pull out. So we did it for the base case 1, right? And now I said, now apply this argument. Assume it holds true for n minus 1. So assume it holds true for 1. Okay. So when you're looking at the case where n equals 2, you can't use this inductive argument. I guess that is what you were getting at. So I take one cow out. There's one cow that's the right color. That it's the same color as itself. I take it out. I put another one back. It doesn't have to be the same color as the original cow. There was no other cow in the pool to compare it to. Right? So that was what implied that all the cows are the same color. So the inductive argument, it works for the base case of 1, but you cannot apply the argument that I used for the case when n equals 2. You need at least 3 cows. I mean, the point is I pluck one cow out. I've got n minus 1 cows here. They're all the same color. I put this cow back. I take another cow out. This cow has to match with the third cow that matched the other cow I pulled out. That's what makes the argument hold. It doesn't hold for the case where n equals 2. Yeah, George.
So you're saying that because when you pull out first one cow, you don't have any more. Like you have 2 cows, right? And you took out 1.
Okay, so for very large n, this was the argument. The argument was I have a large group of cows, right? So I'll take one out. I have n cows. I take one out. I've got n minus 1 cows that are the same color. Okay? I put this cow back and I take out a different cow. And there was a third cow in here that I could use to assure that they were the same color. Well, there's no third cow in there when n equals 2. I mean, that's why the inductive argument breaks down. I kind of stated it in a vague way, because if I showed that, it's obvious why. So you got to be really careful when you use these inductive arguments. That's sort of the point. Question? Here's another interesting problem. George.
And I've seen other books that in inductive step, you actually assume that it's true for the case n, and you have to prove for n plus 1. Same thing.
I mean, yeah, that's just variable substitution, right? I minus 1 and I and I. Okay, here's another really cute problem. There's a village where all the people either wear a red hat or a blue hat. The village has no mirrors, so nobody knows the color of the hat on their head. And they all meet in the village every day. In the morning, the whole town gets together. They're all very good at counting, okay? And these people are fanatics, and if you find out the color of the hat on your head, you have to go home that night and kill yourself. Okay? So obviously the next day you won't show up at the village meeting, and you only skip the village meeting if you're dead. Okay? Someday some visitor comes to the town, right? And it's either the case that everyone's got red hats or everyone's got blue hats, or there's a mix. Okay? So the villager makes this general observation that day when they all come to the town meeting. The visitor says, somebody has a red hat. And let's suppose the visitor never lies. Okay? You can prove by induction if there are L visitors with, what did I say, somebody has a red hat? Is that what I said? You can prove by induction that if there are L people in the town that have red hats, then L days later, they will kill themselves. And the day after that, the people with blue hats will kill themselves. Okay, and again, it's a proof by induction argument. Okay, so if you live in a village where you're all fanatics, maybe it's not so good to be at math, because this only works if you know that everybody else is good at math too. If everyone, so do people see why that's the case? So suppose there's only one villager with a red hat, right? Then everybody else sees that red hat. That villager sees no red hats. Or as far as that villager knows, everyone has a blue hat. So when the visitor came to town and somebody has a red hat, that villager knows it must have been them. They go home that night and kill themselves. And then everybody else comes back The only red hat's gone. That guy killed himself. He must have known he was the only red hat. Otherwise, he would, if there were two red, if I saw that the guy who killed himself had a red hat, if I also had a red hat, he would have seen the same thing as me. He wouldn't have gone home and killed himself. So he must have been the only one with the red hat. So then all the blue hats, they know they must have a blue hat. They kill themselves the next night. Okay? Now, what if there were two villagers with red hats? Then everybody would see another red hat. They wouldn't kill themselves on the first night. Right? But everyone shows up in the village the next day. There are two villagers. Each of them sees only one other with a red hat. Well, that other one with the red hat would be dead if they were the only red hat. So now, two villagers with the red hats, on that second day they know that they've got red hats. And they know that they're the only two with the red hats. Because they see one, they have one, and they don't see any others. They go home on the second night and kill themselves. And everyone else comes back the next day, they know they got a blue hat, they kill themselves. And so, etc. So if you have a red hat, and there are n other villagers, if there are a total of n villagers with red hats, then you see n-1 other villagers with red hats. And if they're the only red hats, they'll know to kill themselves on the n-1st night. Right? And when they come back, if they kill themselves on the n-1st night, you know you must have a blue hat. If they don't kill themselves on the n-1st night, you know you must be a group of n with red hats. So you go home and kill yourself on the nth night, along with everybody else red hats. So it's just kind of interesting that a villager can come in. Suppose you have a red hat and you see 5 other red hats. The villager can come in and say, somebody has a red hat, hasn't told you anything new, and it still sets off this reaction where you have to kill yourself. Because you're good at math. I mean, the irony. Because everyone in the village is good at math. So, the moral is, having a country that's not so bright, maybe it's a good thing? I don't know. It's a politically motivated comment. All right, think about it. Okay. I don't believe that, I should also add. Okay. Hence, my strong desire to educate people. Because I think a country of smart individuals is good and good at math. All right. We digressed. But hopefully everyone understands induction a little better. Anyway, so you can use proof by induction. Okay. Where are we? Claim that every tree has at least one leaf. Let's prove that. How are we going to prove that a tree has leaves? Any ideas? So proof that there are edges. A graph that's connected and has no cycles has to have nodes with only one edge. Any thoughts on how to prove? Yeah, I mean. Okay, we prove by contradiction. Okay, so what? Well, huh? Has to be a cycle, yeah. Let's see why. So the idea is I'm going to start at some node that's not a leaf. Okay, call it B1. And I'll take an edge. I don't care which. To some other node. Okay? It's not this edge. This can't be the only edge to this node by the assumption. So this node has some other edge, right? So I'll take, if it has more than one other edge, I'll pick one arbitrarily. But I'll take some other edge and I'll go to some other node. I get to the next node. Again, it's got to have another edge. So I'll take that. So because there are no leaves, every time I get some node, there's some other edge going somewhere else, right? That's always got to be true. So I just keep doing that forever. The graph has a finite number of nodes, right? So at some point, I got to go back to a node I've already visited, right? I mean, every time I get to a node, I go to some other node. Eventually, I run out of nodes, and I got to go back to some node that I've been to already. There's my. You see that? So more formally, build a path P as follows. So treat T, I should say, with n nodes. All right, with no leaves. Okay, so should have said let T have n nodes. Okay, build a path P as follows. Start at some arbitrary node. N0. It's called P0. Okay, then P sub I. So let's say I equals 0. P sub I must have more than one edge. Take an edge other than the one used to arrive P sub I. Okay, and because T is a tree, there are no cycles. So P sub I plus 1 cannot equal P sub I minus 1 all the way back to P0. Right? But P sub n minus 1, P sub 0 is a sequence of n plus 1 nodes, hence two nodes must be the same. There's your contradiction. Okay? And claim 2. If a leaf node and its connecting edges are removed from a tree T to produce a graph T prime, then T prime is connected. Okay. Claim 2 proof. Again, we can prove that by contradiction. Suppose you have a T with leaf node n, and removing n and its edge creates an unconnected graph T prime. Okay, so what does it mean for it to be unconnected? Then there exists nodes I comma j in T prime without a path from I to j. Okay, so the path from I to j in T had to have passed through n. Right? I mean, I got rid of this node. If the path didn't go through n, then that path still exists. And use that removed edge. Okay, but that's a contradiction. Right, I mean, basically, I've got some I and I've got some J, and along this path I have this node N has only one edge connecting to it. So why would I take this edge, get to N, and I get stuck? I can never get to J, basically. So by removing this, how can I possibly segment the path? I mean, basically N had to somehow lie on that path, and I had to go in through one edge and out through another, and then N wouldn't be a leaf. So that proves the. Okay? So there you go. There's your proof by induction that every tree with n nodes has n minus 1 edges. And let me just, I did define subgraphs. Let me do a subgraph. A subgraph G prime of a graph G satisfies G prime equals V prime E prime, where V prime is a subset of V, maybe equal E prime is a subset of E, right? And edges in E prime connect some nodes in E prime. So basically, you start with your original graph G. You remove some nodes. You remove any node you remove, you have to remove all edges connecting to that node. But you remove some nodes, you can remove some edges, and that's a subgraph. So I just use that term, and we're going to use it frequently. So, okay, and let's stop. So again, if people have questions about the midterm, if you want to come by at like 11:40, I can answer some questions then.